so we talked about, at the last lecture, we talked about how energy is kind of an unsolved problem. We have good estimates for energies, but it's still a little bit open, and these are all models. None of them are perfect. We talked about how molecular mechanics uses an additivity assumption. We have different terms that we add together. The first separation is local and non-local energies. So we talked about bond energies being springs. We talked about angle energies being on springs. And we talked about torsion angles also being with simple spring models, right? So all that we talked about last week. And I pointed to some references there. What I want to go through today are the non-local forces. So always two atoms, say on different ends of the protein as they come near in space, how they're interacting and feeling each other. And you gave me a really nice list last week. You guys had a great list. So we'll go from there. So the first one I want to talk about, kind of in order of importance and simplicity to more complex topics. Did you have a question?
Yeah, maybe it's just a little semantic. I was wondering what you're referring to as like local and non-local versus like a physical and chemical type.
Yeah, let's see. So the local, it means local in chemical sequence or chemical connectivity, things that are directly bonded together or a few atoms away. So those local or bonded terms are the bond energies, the bond angle energies, and the torsion angle energies. Those are what I'm calling local or
yeah, so I understand that. Because I know I just heard it with a different terminology. I was just wondering if there's like a difference in like the perspective or sort of approach that people take to understanding it, or is it the same thing?
What do you think? So, yeah, we'll go through a few approaches to understand. I mean, so those forces all look like energy versus some variable, and basically had a minimum, and then as you move away, and any function we can approximate near a minimum is a quadratic. So it's really an approximate. It's a local approximation, knowing that we know the most stable solution and approximately the stiffness of these. So those aren't, even though these are quadratic, it's not, beyond that, there's not a lot of rigor in how that potential surface looks. You can get those out of quantum mechanical simulations, so you can take small molecules and you can stretch the bonds and you can calculate energies from that. So there are theoretical ways of coming up with that, and then you can also pull that out of like spectroscopy data.
Okay. So I have a second question. So for the quadratic approximation, within like how many kT of the minimum is it a quadratic?
You'd have to go to the literature and read something. I'm sure there's things both from the theoretical side and the experimental side on this, and I'm not totally sure.
Okay.
I'm not totally sure. I think a harmonic is a pretty good approximation for the kinds of things you see in a normal fluctuating protein in solution. I think where it would be really important is if you were looking at a reaction, so you had a nucleophilic reaction or had some kind of decomposition where you're pulling a peptide bond apart. Now you have to get up over this barrier and let it break. So then the shape is going to be pretty important. That you're not going to see in a traditional molecular mechanics or molecular dynamics simulation. And then Rosetta's not going to worry about that. Our Monte Carlo approaches, design approaches, won't worry about that because we're not going to follow this process. We're just going to remove an atom and put a different side chain on. Yeah. Does that help?
Yep.
Okay, so I want to start with van der Waals forces. Okay, so van der Waals forces basically is the first force. It's important because it says that neutral atoms are going to attract and come together and interact. So I think most people have heard about this. We talked about this last week briefly. Just as a review, you probably remember from your thermodynamics class or your physical chemistry class of hearing of van der Waals looking at a gas law, PV equals MRT. And the van der Waals equation of state, so van der Waals took that ideal gas law and adjusted it for real gases to look like P plus A over V squared times V minus V equals nRT. So it's a correction for the pressure adding some and the volume subtracting some. So in an ideal gas, you have point atoms that move around and don't feel each other at all. So the two corrections here is One is that besides, not only that are these not interacting, now there's an attraction between atoms. And it depends on the distance between the particles. As you increase the pressure, that effect becomes larger. The other one here is that atoms have finite size. So if there's a correction, it's not just about volume, but there's some volume that is occupied by the atoms themselves. So those are the two effects that will come under van der Waals forces. There's really two things going on here. One is this attraction, and two is this repulsion. So the attraction comes from, you remember what the attraction come from? Why are there attractions between otherwise neutral atoms? It's now quiet. Everybody knows they're just not speaking.
Dipole attractions, temporary dipole.
So these are induced dipole, induced dipole interactions. So these are also known as London dispersion forces. And basically have two neutral atoms that are near to each other, and just because the electrons are floating around and they're somewhat correlated, you might get something of a dipole on one of the atoms, where maybe there's more positive charge, more negative charge at different ends, and that would induce a dipole in the nearby atom in the opposite direction as the opposite charges attract, and then that in turn would induce forces on the first atom. So these are completely neutral atoms, but they have some kind of attractions because of the correlations in the electrons. So you can get this between permanent dipoles also, or permanent dipoles and induced dipoles. In fact, the functional form is very similar, but you can do this completely with neutral atoms. So in general, to do, not do justice to the math, but to briefly go through where the scaling comes from. So if you have a fluctuation in a dipole, that would be a vector quantity p pointing in some direction in space. Say that's on this first atom P1. A dipole, an electrical dipole, creates an electric field. And the electric field that comes out of particle 1 is going to be proportional to that dipole, but it's going to decay as distance cubed. So that, it's like a point charge decays as 1 over r, a dipole is going to decay like 1 over r cubed. Then on the other side, the second atom will experience a dipole that would be induced by this electrical field. So it's going to be proportional to, so equal to some I'm forgetting the word now, but some kind of polarizability. The polarizability of atom 2, multiply that by the electric field it feels, and that'll tell you how much dipole will be induced. And then that field itself will, that dipole will create a second field that will go like P2 over r cubed. This is a little bit hand waving. The combination of this isn't exactly straightforward, but it's somewhat similar to the product of this. So at the end of the day, the resulting interaction goes like some constant divided by r to the 6th. Okay, so if I were to plot energy versus distance at far away distances, this energy goes to 0, and then as you get closer and closer, as r goes closer to 0, this becomes a larger and larger force. So this is some constant over r to the 6th. and it's negative because it's attractive. Okay, so the London dispersion forces are purely attractive, it's pulling things together, yes.
Just to make sure that E with the vector is an electric field and the other E is an energy.
Yeah, you're right. This is an electric field, this is an energy. This is the London dispersion forces energy. Yeah, thank you. All right, then we typically, so the London dispersion forces are then typically combined with the repulsions. And the repulsions arise from the Pauli exclusion forces. This is the same one from quantum that says two electrons can't occupy the same state. Things can't overlap, can't be in the same place. Atoms cannot occupy, let's say electrons cannot occupy the same quantum state. And from that, it's going to turn out that the atoms cannot overlap. Which makes sense on a macro scale. Things can't be in the same place. In the atomic scale, in the weird quantum world, that might not necessarily be so, but it is true that you can't necessarily have these atoms in the same place. One of the best ways to model this is with the Buckingham potential. Which, to my understanding, is supposed to be the most theoretically accurate. It looks like that the energy goes like some constant. There's E to minus B prime R. So the energy is basically an exponential in 1 over r, and it goes up to infinity exponentially. There's energy and there's r. So as you get close to overlapping, there's this exponential repulsion between the atoms. In modeling, these typically get put together in something called the Lennard-Jones potential. So this is van der Waals, London dispersion forces plus Pauli, an easy and expedient formula. So the potential van der Waals, let's write this energy. Typically sum over every pair of atoms, so all ij pairs of atoms. Sum epsilon ij, sigma ij over rij to the 12th minus 2 sigma ij over rij to the 6th. Talked last week, we mentioned this article by Neria, forget the year, but this is equation B3A in Neria. So Neria, this is coming out of Martin Karplus's group, again Karplus of the Nobel Prize last year. So this is one of the original formulations for looking at van der Waals in molecular dynamics, traditional molecular dynamics simulations. And so Neria has this equation, and it has the parameters for epsilon and sigma, and then the r is the distance between the atoms I and j. So what else? Sigma ij is going to be sigma I plus sigma j, or ri min plus rj min. These are essentially the radii of each atom, the van der Waals radii, and we add together the radii for each atom, and then that gives you a diameter or equivalent distance between the two atoms. So typically they're done just by adding. either in this table as sigma, or sometimes they're done as the minimum distance between two atoms that you see from experiments or from data, structural data. The other mixing rule we have is EIJ is the square root of EI, EJ, epsilon I, and epsilon J. So this energetic parameter there, this is in units kcals per mole. This is in units of angstroms. So the sigma is essentially is a scaling parameter, how close things can be. This R over sigma will be dimensionless, and same thing here. And then the epsilon will put the energy units of kcal per mole on that total energy. Right. Myria does this with what's called a united atom model. So we will do what we would call as lumped nonpolar hydrogens. Myria has lumped all of the hydrogens into the carbon atom. So we have a CH pseudoatom and a CH3 pseudoatom. We have an oxygen atom, and because this hydrogen is polar, we want to place it where it is, so we put that hydrogen on separately. But these hydrogens we don't bother to place, so it's a little bit like your shorthand diagrams that you might draw on a molecular structure. It turns out in a lot of X-ray structures you can't see these hydrogens anyway, so they're a little bit to know exactly where they're placed, and this is a nice way of kind of jumping up the length scale. All right, so what does this potential look like? Energy versus distance. We're going to have this attractive piece that we had from the attractive, 1 over r to the 6th piece, and then at some point the repulsive piece is going to take over, which in the Lennard-Jones is this 1 over r to the 12th. In the theoretical, the Buckingham potential is this short range repulsion. We get on that exponential term. So we'll have this region of attraction and this region of repulsion. All right. Can you tell me what point that is? Where's the Lennard-Jones potential at a minimum? How do I figure it out?
Is it bond length?
Say again?
Bond length? Bond length.
Bond length. Well, so these aren't chemically bonded.
Oh, that's correct.
These aren't chemically bonded. These are things that are just interacting through space. How about mathematically?
So, where the R equals sigma.
How do I find the minimum of a function? Set the derivative equal to 0. D, E van der Waals, or E Lennard-Jones, drij equals 0. Everybody do that in their head real quick. Really trivial, actually. This should come out to sigma ij, because we'll get a factor of 2 between these different exponents that we bring down in the derivative. So the minimum is going to happen at sigma ij. Can you tell me what the energy is when rij equals sigma ij?
I mean, it's relative, right?
Negative epsilon ij, so the sigma over r is 1. So we've got 1 minus 2 is negative 1 times epsilon ij. It's actually pretty simple when we put it in this form. So what this says is these radii, what they mean, that the sigma radii or the sigma ij, that's the distance where these atoms are going to be most happy, where they have enough attraction and they're balanced with the repulsions. And with the attractive and repulsive forces are balanced, and minus ij is how much energy you get from those two atoms being close. So it's a very convenient form to use mathematically. It's also part of the reason we use this is it was made up in the 70s. In the 70s, the computers were fairly slow, and you tried to be careful with every operation, so you didn't want to do too many multiplications. One thing that's convenient here is once I calculate sigma over r to the 6th, I can just square it and I can get this one here, right? So I have a nice cheap computational operation, so that the computers and the speed of the computers drove scientists to use this approximation, and now we're kind of married to it because all our parameters are in this form. The Buckingham potential is theoretically better. There should be an exponential. There should be a slightly different shape here. On the other hand, it doesn't matter all that much. We have a nice steep slope here, and for all practical purposes, the atoms kind of stay in this range. They don't get too close. So it's not a bad approximation either. Okay, so let's see. I guess the remaining question is where do we actually get these parameters from? Well, practically for you, you can get them from Myria, because Myria's published these. As scientists, where do we come up with these? Well, there's a few things we can do. One is looking at small molecule studies, so we can take small small hydrocarbons, and we can measure thermodynamic properties. So we can look at vapor boiling points and vaporization energies, where you take a liquid and then boil it, and they become far away. The energy there, a lot of that is van der Waals forces driving liquids together. And we can try to match that up with the energies. The distances we can get from spectroscopies or calculations of density and molecular volume. And then, so that's kind of from the small molecule energetic measurement, and then we can scale these up. The other thing we do is come from proteins, and so we can look at the protein data bank, and we can look at how close are atoms in the protein data bank and try to make some inferences about what the van der Waals forces are from there. Okay. All right, questions about Lennard-Jones or van der Waals?
Yeah, quick. So what is the reference point for like the minimum energy?
It's a great question. Yeah, so the reference energy is far away. This goes to 0, so things aren't interacting when they're far. What are you asking about this point? What do you mean? What is the so this point
I guess you
is
just
relative to far away.
to no
So
interaction.
far away to here, this change in energy is how much energy you gain bringing these together from far away to where they can feel each other. Does that answer the question? Other questions? Okay, so in the homework, one thing I've asked you to do is just run through the motions and look up an atom and some distance and plug these out so you can see where the equations come from. Open up those articles and look at them. And you'll do those for each of several potentials. Very important for protein structure, right? So let's look at, say, a beta sheet or an alpha helix. I have an amino proton wrapped in a hydrogen bond with a carbonyl. This is going to happen every time we have an alpha helix, and every time we have a beta strand, we're going to have these hydrogen bonds that zip up the backbone, right? So obviously, this looks pretty important. The energy of the hydrogen bonds should be important to figure out for protein energetics. Okay, so where does this force come from? Is it just electrostatic? So this is a little bit positively charged. This is a little bit negatively charged. There's an interaction there.
I think it's a little bit covalent.
It's also a little bit covalent, right? We always draw these with kind of dotted lines. It's almost like a bond. It's not as strong as a bond, but it's definitely stronger than electrostatics alone. This oxygen, in this case, is an sp2 hybridized oxygen, so it's got a couple spare orbitals hanging around, and this proton, some of the electrons are withdrawn to the nitrogen, and these electrons are going to come over and share some of that bonding space, share some of that S or sigma bonding orbital that could be occupied between the oxygen and the hydrogen. So we have a partial covalent also has some aspects of dipole and electrostatics in it, but it's different than just straight dielectrics. Okay, so if you look at protein structures, all H bonds are satisfied in buried protein sites. This is a result from George Rose over in the biophysics department, who's looked at lots of structures and did a lot of computational analysis. He looked at all structures and all potential proton donors and proton acceptors. They're all paired up pretty much inside structures, at least within a little bit of error, which might be the error of the crystal determination. So given that things that are on the surface of the protein, not necessarily so, because what does it hydrogen bond to if it's on the surface of the protein? It's a solvent, right? So if this wasn't protein here but water, there could be a water molecule. So they're all pretty much satisfied. So that seems important. However, how much energy does it add for protein folding? That's a question. So let's say we have a hydrogen bond buried in the protein. If we break that hydrogen bond, say we unfold the protein, take a beta sheet and rip it apart, now I'll have this NH on its own, and I'll have this carbonyl on its own. So what happens to that proton and that those empty orbitals of the oxygen? We now expose it to solvent, yes?
The hydrogen bonds of water.
We're going to hydrogen bond here with water. Same thing with this oxygen. This can hydrogen bond to water. What happens to those waters when I zip up the beta sheet? I have two waters here. If I break these hydrogen bonds, I have those two hydrogen bonding sites, so I can put those back together. So when I have the protein hydrogen bonding, I have two solvent molecules binding. When I pull the protein apart, I hydrogen bonded two solvent molecules. So this is roughly two hydrogen bonds, and this is roughly two hydrogen bonds. So what's the delta energy between those two? How much energy does hydrogen bonding add to protein folding? What does it look like?
Zero.
Looks like zero, right? So is it zero? Well, there's certainly, in this game, there's certainly no net gain of hydrogen bonds here. You fold things, you
No,
don't.
we say that about enthalpy. You can say enthalpy is 0. Why is delta G 0?
Yes, okay, you're right. So there could be some entropic terms, whereas these waters are interchangeable when mixing around with other waters. So you're right. Maybe we want to say internal energy or enthalpy. Maybe 0. You're right. We don't really have the entropy in here. Okay. Well. So maybe this is true. Maybe we don't get a lot of stabilization out of the hydrogen bonds. One thing I do know when I do protein structure prediction, when we fold the protein, well, okay, in nature you have this, all of these hydrogen bonds that George Rose has analyzed in the protein data bank, they're all made. Everything buried makes hydrogen bonds. When we're in the computer and we fold a protein or we dock proteins together, we don't necessarily make hydrogen bonds. So in the computer, we can make all these structures, and we might end up with pouches that are unsatisfied. Well, that's definitely worse than both of these scenarios, right? So HBs are definitely better than unsatisfied H-bond atoms. So if I were to compare this to a third situation where I have these buried and I don't have space for the waters, that's definitely bad. So as far as an energy to compare different folded states, it's a little bit of a question of what the reference energy is, and those unpaired hydrogen bonds inside are certainly worse. Metrization. How do I evaluate the energy of a hydrogen bond? Well, it is partly quantum, so it depends on the orbital and satisfying the orbital. So I'm going to make a hydrogen bond donor here that's donating a hydrogen atom. I'm going to have that hydrogen bonded to an acceptor atom. So here's a hydrogen, it could be on a nitrogen, it could be on an oxygen. The acceptor could be, again, a nitrogen or an oxygen, anything that can accept a proton, has a free pair of electrons. And we're going to have an acceptor base atom that acceptor is latched onto. So if this is, say, the carbonyl oxygen, this would be the carbon. And that's going to go back to the rest of the protein, and this is going to go back to the other protein. Okay, so there's my geometry for the hydrogen bond. What parameters are important in the energy? Well, certainly this distance, I'm going to call that delta HA, the distance between the hydrogen and the acceptor atom. This angle theta, the bond angle around the hydrogen from the donor to the hydrogen to the acceptor could be important. This bond angle psi from the base atom to the acceptor to the hydrogen could be important. And then we call this angle chi, this rotation angle, or the torsional angle rotating this hydrogen around this bond axis in the board, so out of the board and back into the board. So those are 4 parameters that was used particularly by Tanya Cortema. We're going to pull some of this model from. And ideally we'd want energy of the hydrogen bond as a function of each of these parameters. The distance, bond angle around the hydrogen, the bond angle around the acceptor, and the torsion angle. Okay, so one way to do this would be to throw this into a quantum simulation, and then we can vary all these distances and we can measure all the energies. And that's been done. One of the challenges is you can do that in quantum in vacuum, but you really want water or protein around it to have the right electrical dielectric field around when you're solving those wave equations. It's a little bit hard to do. The quantum would capture all of the things that people were talking about: electrostatics, dipoles, induced polarization, exchange repulsion, charge transfer. All of the underlying quantum effects of filling that orbital would be captured by a quantum simulation. Another way of doing this is using a statistical model. It's also called knowledge-based potential. And I'm showing you this partly to contrast with the van der Waals, where we have a derivation based on electrostatic forces and induced polarity. There you get a theoretical expression. This is one that comes completely out of knowledge. So the way this works is the energy of a hydrogen bond is going to be opposite kT times the probability of observing the distance, the angle, the other angle, and the torsion angle. We're going to normalize this by some random probability based on these same parameters, whereas the random probability we're just going to assume that this is equally distributed in space. So as the distance gets bigger, there's more surface area where you could be making a hydrogen bond. So we have an R squared correction. As you go out further, you're going to see R squared. The number of atoms are going to go like R squared. We're also going to have a sine theta and a sine psi correction. So we'll have that basically as you look, if you look at, say, longitude around the Earth, there's a lot more part of the Earth at longitude 0 than there is at the North Pole, which is just a point, right? So you have to correct for that as you look at these geometric parameters. So same things here. If you go psi goes to 180, there's going to be no, only one point there, but in between, right, 90 degrees, there's lots of angles to come in at, so you have to do some geometric corrections. Okay, so we'll talk about this formulation a little bit more in future classes, but in general what we're doing is we're going to say if we see it a lot, that means it's a low energy configuration. And the, whoops, I missed the natural log tonight. KT times natural log of the probability observed over the probability random. There should be a natural log in there. So this, yeah.
Is it only taking the natural log of the P observed or both?
Of both. Let's see. Yeah, so this comes from statistics. You can do this with statistics or statistical mechanics. That the natural log of a probability should be proportional to some kind of free energy. Okay. Again, we'll talk about this a little more as we go. So one of the approximations then you can make is you could say this probability based on these 4 geometric parameters. You could see, you could make the approximation that these are separable. So maybe this is KT natural log, probability of seeing delta, probability of psi, probability of chi, probability of theta. And we can put all of these over the probability, the random probability, delta, probability random of psi, probability random of chi, probability random of theta. Then the natural log of a product can also be looked at as the sum of the natural logs. And this KT natural log P delta plus natural log P psi plus etc. So we can look at these pieces individually, including the denominator there. And then we can separate these, each of these natural log pieces we can look at as individual energies. So we can take the energy of the hydrogen bond equals some constant that I'm going to call WHB, the KT, times an energy according to the distance, plus an energy according to psi, plus an energy according to theta, plus an energy according to chi. Energy delta HA would then be opposite natural log of the frequency of seeing in a protein, delta HA, divided by the frequency in some random set of seeing delta HA. So in this case, this would be opposite natural log. This would be some count of, well, so this would be this frequency delta HA divided by this R squared, because again, as you the random as you go out in space, the surface area of the sphere is going to go like R squared. There's a constant here. We're not going to worry about it because we're going to reweight the constants later. We're going to lump that outside. All right, so we can also do this, etc. for each other term, the energy of chi and theta and psi. If we look in Portema has tables for all of these quantities and methods for collecting all of the statistics. The data looks something like this. If we plot delta HA versus the frequency of seeing that distance, we get 1.95 angstroms. There's basically a Gaussian distribution of distances of the hydrogen bond. It goes out to about 1.75 angstroms and about 2.05 angstroms. So there's a standard deviation of about 0.15 angstroms. Yeah.
So, what molecules
Go out
do you
to a certain distance on this sphere. The surface area of the sphere is for pi r 4 pi r squared. Right, and then if you look further out, there's more area on the surface of that sphere.
Yeah.
So just by random chance, if I look, is there a proton close to this acceptor atom? The further I go out, the more protons I'm going to see. So I'm going to correct for that volume. Let's say basically at any differential point in space, what's the chances of seeing these there? Does that make sense?
Okay. But does it account for that, like, the interaction might be weaker when it's further away?
Not the geometric part.
Okay.
That
Okay,
should-
so this is just geometric.
That's right. So the R squared correction is just geometric.
Okay.
And then these statistics tell me what I see. Plotting here, how often do you see a particular distance when you do this? So if you go out far enough, you'd see many more pairs of oxygens and nitrogens that are 6 angstroms away, just because you're packing space and there's a lot there. So part of this correction is to get rid of that, the fact that there's more there. Yeah, so these statistics get messy as you go out, but otherwise you get, it'll be skewed toward the larger distances just because there's more space there. Okay, so the histogram makes sense. The most common hydrogen bond length is just short of 2 angstroms, and then you get a little bit of variation there. That's the energy, and then what you can do is from there, if you take the opposite natural log of the probability, it's going to be opposite, so we'll get a negative energy, but we'll get a well around that same 1.95 angstroms. We'll get low energies where the probability is maximum. Okay, so the statistical mechanics work out that if you just sample from this using an energy of KT, so there's random fluctuations in energy, you would get this kind of statistics. This kind of statistics imply that you have this kind of energy potential surface. I think theta should be, what theta should we observe if we look at all proteins? So theta is the angle around the hydrogen, from the donor to the hydrogen to the acceptor. What angle do you expect to be most probable?
180.
180. So it looks basically like that. Great. So this is true if we look at side chain hydrogen bonds. Let's do the frequency according to psi, the psi angles. What do you expect for psi? Let's say we do it for an sp2 hybridized acceptor atom, say carbonyl oxygen. What do we expect psi to be if A is sp2? I think I heard 120, but it's actually fairly broad. It goes from about 90 to 150. There seems to be some flexibility. This is if I look at sp2 acceptors. This is for side chain hydrogen bonds. Let me show you a different one. There's also another curve that in their paper that looks like this. This is for alpha helical backbone hydrogen bonds. Which is the right potential? So if I tabulate all of the hydrogen bonds in alpha helices between backbone atoms, so the backbone carbonyl and the backbone nitrogen. The distribution comes out more over 150 and it's skewed to the right toward 150. If I look at them between side chains, they're centered around 120. Why is that? From the hydrogen bonds, but from what else is going on in an alpha helix? Right, so an alpha helix, you got basically this ladder of hydrogen bonds going up between various loops. What else is happening? Is it just hydrogen bonds that drives that structure? It's trying to make this helix to make all of these interactions work, but it doesn't have total freedom to move these things around. There's only so much flexibility. So it can move it close to the 150 degrees, but it's not quite, it can't get down to 120 degrees. It's hard to make these fit and still have the geometry of the helix come together. So it's just one of the forces that's balanced together. All right, so it comes down to a balance between different forces, and this just so which is the true potential? So the side chain might be more of a true potential. Those are off at the end of side chains, they're flopping around, they're coming from different random directions. There's not other local connectivity of all of these in-between bonds that connect, that constrain these. So you don't have those bonds waiting in place. So the side chain is probably more representative of what the underlying quantum mechanical energy is going to be. Let's see, there's one more. Look at the frequency based on that chi angle. So now we're spinning around here. If we do the SP2, the chi angle tends to be closer to 0 and closer to 180, so it tends to be flipped up and flipped down, as you might expect from the SP2. But it's not too strong, and if we look at the SP3, it's totally flat. The SP3 doesn't really. Electrostatics. Okay, so electrostatics are a little bit tricky. So in physics, electrostatics are really well understood. I imagine most of you could tell me the equation for electrostatics. In proteins, they're very controversial because the formula you get from physics is not always the most reliable. Sometimes it's very noisy. It can be prone to a lot of error, and it's well, there's a fundamental problem that we don't know the dielectric, which is the main constant in the equation. So what else? It's also compensated, just like the hydrogen bonding, it's related to hydrogen bonding. As we know, there's an electrostatic piece to hydrogen bonding, so how do we decompose those two? It's also related to solvation, the fact that waters have a lot of charges and nonpolar things don't, so it's related and compounded with all of this together, so it can be challenging to figure out. Well, let's start with the physics. So in physics, if we have 2-point charges, so one positive ion and one positive point and one negative point in a uniform dielectric. So that means there's some dielectric material in between through which the electric field propagates. It tells you how strong that field can propagate and how much it can polarize the medium. Then Maxwell's equations can quickly tell you that the electrostatic energy is 1 over 4 pi epsilon naught, where epsilon naught is the permittivity of the vacuum. So it basically puts the constants in there for us. Times Q1, Q2, so that's the charges of the two, the magnitudes of the two charges, divided by the dielectric of the medium times the distance between them over epsilon r. We put these into units that are convenient for proteins. We get 332 kcals per mole times angstroms over electrons squared times Q1, Q2, both in units of electrons, how many electrons there are, divided by R, the distance between them in angstroms, and then epsilon, that would be the relative permittivity relative to the vacuum. So epsilon equals 1 in an oil or in a vacuum, in water, because water is very polarizable, epsilon equals 80. And now the confounding part is in proteins, epsilon equals question mark. So if we're inside a protein, we have two ions. How much can that medium rearrange electronically to accommodate the electric field? Well, a protein's kind of like oil. It's a lot of hydrophobic in the middle, but every backbone has an amine group and a carbonyl group, so there's a lot of polarity there too. Proteins also move. Water penetrates into proteins. They can rearrange. There's all kinds of things going on. Over in biophysics, Bertrand Garcia Moreno has made his whole career about, well, the last decade at least, about figuring out what epsilon is and how you might model it in a better way than just a single number. Really, the real answer is there probably isn't. It's nearly a poorly posed question. It's not like you have these two ions in a consistent dielectric. It's really this complex medium, so it's more complex than this. But in the computer, I've got to put an energy in. So this is a nice, convenient model. If you're a physicist, if you have a penchant for physics, you like this. It's really attractive because it's, it's so soundly theoretically based on Maxwell's equations and on all of electrostatics. Many charges on a protein. Every oxygen and nitrogen has some kind of charge, and even the carbons have a partial charge, right? So there's lots of charges in a protein, and there's also charges in the medium. So what do? We need to sum over all of those charges. One way of doing that is what's called the Poisson-Boltzmann equation. So this again comes from your Maxwell equation in electrostatics. It's a vector equation that looks like this: del dot epsilon del psi equals rho. That's the Poisson equation. So this is the psi is the electrostatic potential. And rho is the charge. As both of these are vector quantities in space, so this is charge as a function of x, y, z in space. It's a field, and psi is again a potential through space. You take the gradient of the potential, that'll give you the electric field. The dielectric tells you how much that propagates, and the divergence of that should be driven by the charge. Okay, so I've got some protein, and it should have lots of charges in it. All of those might be points where we have charge in the protein. The other thing, this equation, that's the Poisson part. That's an exact equation. The other thing that's going to happen is if there are charges here, there is salt in the medium, right? There's sodium chloride, so there's positive and negative ions. If you have positive charges, they're going to be compensated by counterions in the medium. Right, so in the Poisson-Boltzmann equation, which is used very often in colloids, the charges are going to be minus 4 pi rho f, where these are fixed charges. Let me write it down here. Minus 4 pi fixed charges minus 4 pi times the salt that's around that's going to be brought in by the fixed charges. So this is going to be 4 pi sum over each charge I, or sorry, each ion I in solution, Ci infinity, Zi q e to the minus Zi q psi over kT. Okay, what this says is that if there's a potential, so the electrical potential, again, the charges are going to drive the electrical potential. If the potential is highly negative, it's going to bring in positive ions. How much is it going to bring in? It's going to be exponentially distributed because this is a molecular stat mech mean field process. You're going to bring things in on average that much. And the signs here are such, what you're going to do is sum, these are sum over salt ions, so typically Na and Cl, could be others, there's potassium and anything like that, but each ion is going to come and be around where the charges are to compensate those charges. So here's psi on this side, and then there's psi on the other side, L squared epsilon del psi. And so now this becomes a pretty complex equation to solve, because not only do we have the vector stuff over here, but we have psi in the exponential and outside over here. So this is the Poisson-Boltzmann equation. It's very useful to look at how ions distribute around a charged surface. And then people have applied this to proteins, hoping it would tell us about the electrostatics. All right, so you don't need to understand all of this math. I wanted you to see the formulation, know where it's coming from. So to solve this, you have to solve this vector equation in space, which means you typically set up a grid in space and you try to solve for this potential everywhere and iterate. So there's a few continuum solvers that have done this. One is called Delphi, which is by Barry Honig's lab in 1986 to 2001. He's developed several versions of this, and so it's been around a little bit while. Okay. And it's basically going to capture these fixed charges, and then this is the screening of ions. One of the issues is you still have to, in this equation, put in an epsilon. You have to put an epsilon as a function of space. So typically people will choose outside the protein, people will choose epsilon equals 80, and then inside the protein, some epsilon p, and the answers will vary tremendously. So epsilon p could be anywhere from 1 to 20 is typically chosen, and as you dial that up and down, it changes how much the electricity. Based on this equivalent sphere, by adding up everything that's around it, you can say it's basically in a sphere that's that big, and then it can do another sum to figure out the charges and the interactions. So this is very quick compared to Poisson-Boltzmann versus PV, and it's tuned to approximate PV numbers. So you can parameterize generalized Born to pretty much match what Poisson-Boltzmann does, but a lot faster. So that's a common choice in the field, is to generalize distance between atoms. So in the DDE model, the distance time dielectric model, you replace epsilon with R, and now you get the electrostatic energy is 332 Q1 Q2 over, not epsilon R, but over R squared. So now the electrical potential goes like R squared because of the screening and because of the this changing of the dielectric constant as you get large. So there are some theorists who've worked on things like this. Ariel Warshel, who shared Karp+'s Nobel Prize last year, has worked a lot on electrostatic models. This is one that's that he's put out and tested a little bit. It's really simple, and so it's actually what we like the best in Rosetta, because it's simple and quick, and can oftentimes be as efficacious as some of the more complex and more time-consuming potentials.